We proceed to the next presenter, who is the Dr. Céline Largeau. Dr. Céline Largeau has an extensive experience as an engineer with Renault Group, and today she is an automotive market leader and force project manager at Jules Verne Institute. The force project, which Professor Dr. Largeau is leading, is about low-cost carbon fiber, which could satisfy the nowadays fiber-reinforced polymer demands in cost-effective, eco-friendly, and sustainable way. And Dr. Largeau, the floor is yours. Please, you're present.
Thank you very much for the introduction. So, hello to everybody. I'm going to present you force project today. The objective of this project is to develop a bio-based low-cost carbon fiber, and I will explain you in 2 minutes the objective and how we will proceed to do that. First of all, this is a force approach. The aim is to design a carbon fiber around €8 per kilogram with specific mechanical properties, a young modulus of 250 GPa and a tensile strength a little bit lower than a classical pan carbon fiber, around 2,500 MPa, and keeping in mind the whole manufacturing process. So if you have a look on the bottom of the slide on the process to develop a carbon fiber, you can see that it's a very long process. First of all, you go through the material, raw material, do the spinning to obtain a precursor, and then you go into a thermal process, different thermal process to obtain the carbon fiber, then the surface treatment and the sizing, and then you have the roll of carbon fiber. And to do that, the process is long, and the cost is important, OPEX are important. You can see on the right of the slide the cost breakdown of the carbon fiber. Nearly half of the price is due to the precursor itself, and nearly the same for the processing. So the aim of both project is to work on different aspects, the raw material aspect, the spinning aspect, and also the carbonization surface thermal treatment aspect to reduce the price by 2 and to reach this design around €8 per kilogram. And to do that, we work on different alternatives to PAN. And what is also interesting and I think important for the future is that we have focus on bio-based recycled raw materials. So the force project team, many people, many industry involved in this project with a complete value chain, with big involvement of chemical raw material industry with Arkema and Nippon Electric Glass, also process industry with Mersen, and a lot of key players in their different area. We have companies from aeronautics with Airbus and Safran. We also have sport and laser with Decathlon. We also have naval industry with Chantier de l'Atlantique. And we also have a big involvement of automotive industry and with a major player in the consortium for Russia. And 2 technical platforms working together, French platform, Canoë, the south of France, and IRT Jules Verne. And we also have a collaboration of French university and laboratory with CNRS. And also we are audited by independent scientific council with retired senior management from carbon industry to help us also into the development. If we have a look on the planning, we have been involved in this project for nearly 6 years now. We start in 2015 with a feasibility study and the investigation for the consortium. And since January 2016, we have been working on the lab and pilot line phases with installation of a carbonization and spinning line in Canoë facilities. And by the end of 2022, the aim is to deliver the go-no-go for pre-industrialization and then industrialization. And the aim is to produce around 4,000 tonnes per year at the beginning in 2024, 2025. As you can see, it's a big project as R&D project as for the moment nearly 20 million euro has been funded, and for the next phases, pre-industrialization and industrialization lines, it's around 60 to 70 million euro that have been to be invested for industrialization of this 4,000 ton per year of bio-based carbon fiber. Some key element and unique value of FORCE project and FORCE fiber. First of all, this fiber has been designed for low cost with the use of low cost and bio-based raw material. I will explain why we have chosen the recycled cellulose in a few slides. We also work on optimization of the manufacturing process and work on low cost process for spinning and carbonization. We have the opportunity to work with green chemistry and circular economy with this recycled local cellulose, and also with the integration of value chain key player of this green economy. 6 patents has been registered yet, and what is also interesting to note is that not only good mechanical properties, but also unique performances has been reached in the project with a lower density than typical PAN for this cellulose carbon fiber, and also good interesting mechanical properties for the thermal conductivity for application that requires a thermal insulation. So not only young modulus and tensile strength, also good improvement in density and thermal conductivity for this bio-based low-cost carbon fiber. If we have a look on the competitor, that's some good ideas of where we are with FORCE project. So the target is to reach this 8 euro per kilogram, and we can compare to other carbon fiber existing at the moment, textile pan, but also a medium and high performance pan. And what we see that we are around half the price of textile pan carbon fiber, and we see no other fiber with the same performance and price level before 2025. So this FORCE fiber could be a good opportunity for different kind of industry: automotive, sport and laser, hydraulic blades, airplanes, cabin interiors, and naval industry. In green, highlighting green is industry already involved in the project, but many different industry that could be interested in this bio-based carbon fiber, and that's why it's interesting to have in the consortium several industry already involved with Airbus, with Faurecia, with Decathlon. So we see that a lot of this industry are already involved and give good input and good target to the R&D project. If we have a look more deeply in the project innovation, so first of all, we decided to work on alternative precursor raw material to PAN. So we have been working for 6 years now on cellulose. We also have some development with lignin and polyethylene. We work on the spinning improvement and on the chemical improvement of the precursor with some chemical treatment to improve carbonization yield. We also work on the process for heat treatment, on temperature tension program to develop and to improve mechanical properties, also to reduce OPEX and CAPEX. And we work on development of new carbonization processes that also would help to decrease the energy cost of the carbon fiber process. And then also we perform some trials on this new fiber on a different application to validate the accuracy for different industrial application. So as I mentioned before, we work on 3 different materials: lignin, cellulose, and polyethylene. And now we are focusing mostly on the cellulose. We managed to reach good mechanical properties with lignin, but not enough in comparison with our objective. So we decided to stop 2 years ago lignin development. And we also work with polyethylene, but we also decided to stop because of the price of the PE. in fact, the P need to have some stabilization process before carbonization with sulfonation, and it was not in the price target of fourth project. So we decided to focus on cellulose. We managed to reach very good mechanical properties. And what is also interesting with cellulose is that it's a very abundant, locally available resource. We don't need stabilization before carbonization, and the properties do not depend on the species. So it's a very stable resource, and that's why we decided 2 years ago to focus on these raw materials. Some picture and some information of on the two line that we are using now in fourth project. So these two, the first one is a spinning line that installed in south of France in canoe facilities last year. This spinning line will be able to enable us to develop the cellulose precursor specific to fourth projects, and more particularly to spin recycled cellulose. The aim of this pilot line is to produce enough precursor to feed the carbonization line, and also to develop our own polymers, our own precursor for carbon fiber. Also to demonstrate the feasibility for further industrialization. And as we can see, the distillation and spinning of this cellulose is environmentally friendly solvent and a continuous process. So it's also a good improvement in comparison to PAN, that we use solvents that are environmentally friendly. On this pilot line, we can produce 3,000 filament roving in wet spinning and 1,000 filament in air gap. And then after we assembling them in 12K. So it's used by fourth project, but it's also open to access to academic and industrial partners for overdevelopment. And after, when we have spin the cellulose, we go through the carbonization pilot line, just a few meters from the spinning line in Canoë in south of France. So you can see on the left bottom of the picture, you can see a roll of cellulose precursor. And then after, we go through different thermal treatment to obtain the carbon fiber. So on this line, we can, of course, carbonize cellulose, but not only. It's also open to academic and industrial partners, and we can carbonize over precursor like lignin, polyethylene, and others. The same as the spinning line. The aim is to demonstrate the feasibility for further industrialization, and of course to demonstrate that we are able to reach €8 per kilogram, and the mechanical properties, the target mechanical properties of 250 GPa for the U modulus and 2,500 MPa for the tensile strength. The line can carbonize 10 tools in parallel, and we can reach temperature above 1,100 degrees, and also in the future we'll be able to go up than 2,000 degrees. And we can produce on this line between 1 and 4 tons per year of carbon fiber. For these two lines enable us to reach very good mechanical properties, and also we are very close to the target price of €8 per kilogram. So these are the last results obtained on the two lines with at pilot scales on the carbonization line at the temperature of 1,100 degrees. We managed to reach a young modulus of 130 GPa, and we are able to go upper than that, and the tensile strength upper than 2,500 MPa. So we managed to reach around 2,700 MPa on the line with a density of 1.5. And at lab scale, because at the moment we don't have the equipment to go upper than 1,100 degrees on the line, we perform some trials at lab scale, and when we go upper than 2,000 degrees on the temperature, we are able to reach the target of 250 GPa for the young modulus, and also to keep a good tensile strength around between 2,200 MPa and 2,400 MPa, with a density of 1.6, 1.7. So the results are very encouraging, and we are now discussing with a consortium to start the pre-industrialization of this carbon fiber. And so there are some discussion in the consortium and to finalize the go for beginning of next year and go for pre-industrialization. So yeah, this was the presentation of forced carbon fiber. So yeah, if you have any question, I'm happy to answer you with, as you can imagine, yeah, some parameters are very confidential, but I will try to answer to your question.
Thank you very much, Dr. Céline Largeau. Thank you. It was innovative, interesting for me personally. Is there any question? Let's give a minute. Yes, we have one from Professor Veronique Michaud. Please.
Okay, thank you. Thank you. It's really nice to see you've gone a long way since the beginning. And I just had a question because you mentioned the economic cost, the target that you have. Do you also place some environmental impact targets as well? Yeah. Because it's also one of the big issues with carbon fibers. And I think, yeah, so there should be some choices to be made, and you mentioned that all along, so I was wondering if you do it in a very formal way as well.
Yeah, we perform LCA studies in the project. So yeah, as you mentioned, it's very important as green CO2 impact is more and more a big issue. So that's why we are targeting to be lower than PAN also for CO2 emission. The use of recycled cellulose is a very, very good parameter. It decreases a lot the impact of on the CO2 emission, and also the fact that we use environmental friendly solvent that we recover. It's also a good point. And the process for the thermal process is a little bit different from the PAN, as we only obtain TARs. There are no I will say harmful gas during the thermal process. Okay. So also we don't need also to have a specific device to treat the gas. So it decreases also the energetic impact and the energy consumption. So of course it also has a big impact on the LCA.
Okay, thank you.
Yeah, thank you. There are quite a lot of questions, so we quickly proceed to the next one from Professor Sanjay Rastogi.
Thank you very much, Céline, for a wonderful talk. I have a question over when you take cellulose to convert into carbon fiber, then do you start with the cellulose fiber? And when you normally, like in polyethylene, if I recall, they do with the decarbonation, this carbonization, which they do, it's all done under the constrained condition of polyethylene. And so if you have to convert cellulose into a fiber, there you normally in the past people were using phosphoric acid, etc., for making the fiber, which was termed as Borcel and so on. So how do you start with?
We start, as you mentioned, we start with the raw material itself, of the powder of cellulose, and then we do the spinning. So you're right, we use phosphoric acid to do the spinning. Yeah,
I see. And then the strength in the modulus that you achieve during the spinning process, does it govern your ultimate properties?
No, I think we are, we are using pilot line. So we need to, as we are in the aerodynamic center, we need to stop the line every night. So we know that we suffer from this everyday stop, and we know that we are able to reach better properties. We do a big run it has a huge impact on the performance. So we know that the properties that I mentioned just before are lower than the property we will obtain at industrial scale, because it's still pilot line, and we suffer from the non-industrial process, and so it's pessimistic performance.
Yeah. My last question: what is the modulus and the strength of your cellulose fiber that you achieve prior to its conversion?
Yeah, it's difficult because we didn't measure on the fiber itself, on the cellulose fiber. We measure on the carbon fiber, but we are very close to or upper that you can find for cellulose fiber in commercial cellulose fiber.
Thank you.
If it can help you to compare, we are a little bit upper.
Thank you.
We can proceed. The next question is from Professor Fernando.
I got two related questions. Are you in a position to tell us what your source of cellulose is? And do you purify the cellulose before you spin it?
We don't have to purify the cellulose. We have to wash the cellulose when it's recycled cellulose. But when it's pure cellulose, or I would say non-recycled cellulose, we don't need to purify it.
The source of your cellulose?
It's coming from paper. It's coming from cotton industry, so recycled cotton or recycled paper. There is it's commercial sources.
Thank you.
And a couple of more questions in QA section. It's a quick technical questions, Dr. Largeau. Do you produce prep laminates using forced carbon fibers?
Yeah, we can. We perform some trials. Yeah, very good with very good results. But yeah, it's some of our partners in the consortium are doing this pre-preg, and some perform from trials very good with very good results. But yeah, it's confidential, so I can't tell you. But yeah, good results. Yeah.
To have them available. The next question is carbonization versus graphitization. What's the cost difference?
It's a temperature treatment. Carbonization, I think we can say that it's you go to 1,500 degrees, and yeah, when you go upper than this temperature, it's graphitization. So it's just graphitization. It's temperature around 2,000 degrees.
Okay, you already answered the next question about the temperature. Thank you very much.